Hello everybody, so we're going to talk about polynomials. Polynomials appear in all sorts of places in the real world. One of the most common examples is in relationship to length, area, and volume. Um, Length is what we call one-dimensional, so when you find the perimeter of something, that's a linear equation. Um, like for the perimeter of a square, it's 4 times the number of sides. So that the number of sides is to the first power. So the perimeter of a square is 4 times s, right? So this is to the first power, so we call this a linear equation. It grows by 4 each time you increase the side length. So if it's side 1, its perimeter is 4. If side's 2, the perimeter is 8. If side's 3, its perimeter is 12. So it increases by 4 each time. It's called a linear equation. When we look at area, that is called quadratic because you can always break things down into square inches, which are four-sided objects. So an area of a square is s squared. Volume we call cubic, which follows, it's the cube of the side length, so s cubed for a cube, right? So if I wanted to find the volume of this cube, I'd find the side length and I multiply it times itself 3 times. Okay. So there are other analogies within the real world. I come from a background of engineering, where I designed bridges and buildings. And one of the things that you do a lot of in that type of engineering is to do beams. So like you put a load on the beam, like the bridge, and it wants to flex down, right? So you have what's called, so like if this is the support, and then you have a uniform load, let's say it's a constant load across the whole thing, right? The weight of the structure itself. So there's a constant load, and then if you want to measure the stresses within inside the beam, so like it's trying to, tear itself apart when you, if you were to cut it, it would want to fall down, right? So that's called the shear stress, and the shear is a linear pattern. It looks like that. And then if you look at the moment, which is how it bends, how is it bending, that is actually a quadratic, and it has a parabolic shape like that. When you look at, it's 0 at the support, right? There is no bending at the support, but its maximum bending is right at the center. And then you could even go further into deflection is the cubic, and even vibration has something to do with the fourth order, which isn't even included here. So it depends on what field you go into of study, but these polynomials show up everywhere in the real world. So it's important to understand how they work. So here's some visual patterns that we could talk about that have characteristics of polynomials. So here's the most simple thing you could do. There's 1, 2, 3, right? So the pattern here is just n, right? So n tells the number of steps, tells you the number of cubes that you will see. So that is what we call a first order polynomial, and this equation is just n. Here it looks like we start with 1, and then we add 2, and then we add 2 more. So each time it's adding 2. If it's having a constant rate of change, that is a linear equation. And so the number of steps included would be, let's see, you're multiplying by 2 because you're adding 2 each time, so 2n. And now I want to make sure that the first step is right, because let's see, if I put in a 1, I would get 2, and that's wrong, so I need to subtract 1. Right, so I think this is right. So 2n, so the first step, if n equals 1, would be 1, and n equals 2. So I put in a 2, and I get 4 minus 1 is 3, so that's correct. And then n equals 3. I put in a 3, it's 6, minus 1 is 5, which is correct. So this is the linear equation representing that pattern. Okay, now is this also a linear pattern? Let's see, it grows by 3, and then it grows by 5. So, from here it was plus 2, and we knew it was a linear pattern. Here it was plus 1, plus 1. Here it's plus 3, and then plus 5. So it's not a linear pattern at all. So actually this is our square, right? 1 squared, 2 squared, 3 squared. So this is just n squared. Let's see, this is 1, then it goes to 4, and then it goes to 4 plus 1, 2, 3, 4, 5. 4 plus 5 is 9. So actually this is actually, we're adding 3, adding 5. This is identical to this one, isn't it? I get the same numbers out of it. And you see that geometric problems all seem to, the geometric problems that are on a flat surface seem to follow this sort of a pattern that it's n squared. And you can even do it with hexagons, which maybe we'll look at a little bit later. Here, it looks like it's three-dimensional, but actually we're only doing one layer. So this is not really three-dimensional. I just try to trick you with that, but this is the problem that we did in the intro, where it's just the triangular numbers. And this one we knew was 1/2 n times n plus 1, or n squared over 2 plus n over 2, or also another equivalent expression. So this is a polynomial with two terms in it. So it has a quadratic term and a linear term. Okay, now we go to three-dimensional, where it's actually increasing the area and the depth, right? The area and the depth. So this makes a three-dimensional thing, and this is n cubed. Okay, so that's a little intro to what polynomials are and how they show up in our real world. Actually, I have one more to look at. This is not a polynomial. This one doubles each time, so n, and it goes up by 1, and then it goes up by 2. And you can see that it's doubling each time, so it gets doubled again. The next one would have 8 in it. So this one's continuing to double. This is called exponentiation, and this is actually 2 to the n power. But that doesn't quite work, because I want to have, if I put in a 1 for n equals 1, n equals 2, this is an off by 1 problem, right? So I need to subtract 1, right? So this is like 2 to the n minus 1. So this is 2 to the 0 would be 1. 2 to the squared would be, squared minus 1 would be 2 to the first, so that'd be 2. Yeah, so this fits out. Okay, so yeah, this off by 1 happens a lot in programming, and you kind of just have to figure out, how do I fix the first step, right? So that's just another example, but this one is not a polynomial.